Hello everyone. Today we are going to start chapter 7, which is eigenvalue and eigenvectors. So I want to show you what we are going to do in this chapter. Okay. So firstly, let's have a review what we did before for linear system of differential equations. Let's take a look at this example. So if our differential equation look like this, dx1 dt, which equals some like fx1 plus 2x2 and plus, for example, 2e to the t. Okay, so and we have another differential equation, dx2 dt, so which is negative x1 plus 5x2 maybe minus sine t, this kind of thing. And we can write this into a vector form, right? So we learned the vector form means what? So x1, x2 derivative equals a and x1, x2 and plus b 2e to t negative sine t. So we also had this in our second meter. Here is a, that means coefficient. So here should be -1 and 5, right? So this is called linear system of differential equation. So in this chapter, we are going to solve this kind of differential equation. Okay. So now let's take a look at eigenvalue, eigenvectors. Before I give you the definition, I want to give you some basic idea of what is eigenvector and eigenvalue. So now let's take a look at if we have function, okay, function y equals fx, which is x squared. So input means x, right? So if we give an input x equals 2, and we get output, which is y value. So y value, if the function is y equals x squared, so when we have the input 2, output should be 4. For any function given input, we have another output. Now let's take a look at matrices like A times V vector, okay? And we call this is the linear transform. Why is called linear? Because A is just like made by some numbers. And here we call this is the output. And this is the input. I'm going to show you one example, okay? So for example, if our A is 1, 3, -2, 0, and if we give our input this one, and when we perform the product, and we get an output. So this is the input, and this is the output. Okay, so why is called a linear transform? If we look at this in graph, we treat this -1, 2 as a vector, -i plus 2j. Okay, this is a vector, right? We just write down in a column way. So -1, 2 should be about here, this vector. Okay. After transformation or after the product, we get a vector like a 5i plus 2j. So 5i plus 2j. So 1, 2, 3, 4, 5, and the 2 is almost there. So we get another vector, 5i plus 2j, and then -i plus, here's 2j. So it's kind of is called a linear transform. So we transform a vector into another vector, right? Into another vector. It's called a linear transform. Now I'm going to give you more examples. So this one is like 0, 1, 1, 0 can transform this vector 2, 3 into 3, 2. And if we draw graph, that means the transformation is like change this vector into the other vector, like this, symmetric. Okay, and let's do one more. 0, 1, 1, 0 transform 1, 2 into same thing, 2, 1. Okay. And the same matrix A, 0, 1, 1, 0 transform like 1, 1 into same vector 1, 1, because the vector is still like a on the line y equals x. Okay, let's take a look at this vector, this transform. So 3, 1, 0, 2. Okay, and this transform this. Okay, and if we do the product, we noticed this is -2 and 2, and we can simplify this vector just 2 times -1 and 1. If I draw the graph, that means -1, 1 should be here, right? And after the transform becomes double of that one, so like this. So the vector for this vector, the transform is going to be this vector, and we call this kind of vector is the eigenvector. It's special, so it's like when we do the transform, it's like when we solve a problem, we cannot solve here. Okay, we cannot solve from here, so we transform into another like a space. We can solve from here easily, solve easily. But under this transform, the vector, eigenvector, that's which means special vector, they don't change. They are like a basic property. Even their length may be changed, but their property, they still be almost the same vector. So this kind of vector is called eigenvector. And when we find the solution here, we come back. Okay, and because that kind of vector doesn't change, so it will help us to find a solution. I know it's kind of hard to difficult to understand from here, but I just want to let you know, like visualize what is eigenvector. Eigenvector, and this number is called eigenvalue. So it just means under a linear transform AV, and it's going to be like a scalar times the same vector. So it doesn't change the position of the vector or direction of the vector. It's only change the length of the vector. So the vector still keep in the same position. Okay, so this kind of vector is called eigenvector. Now I'm going to give you the I'm going to give you the definition. Okay. Now let's take a look at definition 1. Eigenvalue and eigenvector. So now we have a matrix A, and this is general matrix, and any value of lambda. So lambda is a scalar here, for which this equation, like A times V, which is lambda times V. So it's same as before. Under the linear transform, the vector doesn't change, still keep the same vector, but change the length. And this one has non-trivial solution. V, non-trivial solution means V cannot be 0. Okay, that means V cannot be 0. No zero solution, because if A times 0, anything will be 0. So it doesn't make any sense, right? So we want to only say that kind of vector is non-zero vector. For the non-zero vector, we have this property. Okay? Non-trivial solution means V is not 0. And those kind of vectors are called eigenvectors. Okay, lambda is called eigenvalues of A, and the corresponding non-zero vector are called eigenvector. Corresponding non-zero vectors V are called eigenvectors of A. Okay, sometimes they are also called characteristic values and the characteristic vector. So that's in some other book. sometimes are called characteristic values and characteristic vector. It's just a different name, but we use eigenvector and eigenvalues more often. Okay, now let's take a look at example 1. I'm going to show you. Verify that a vector is eigenvector for a given matrix. So let's see. Verify that this vector, which is 1, 3, okay, is, let's keep it consistent. We just use the parentheses. Doesn't matter too much. You can use the, break. You can use this way. It doesn't matter too much. Is an eigenvector of this matrix A. 1, 1, negative 3, 5. So what's the meaning of this? We just perform, we just want to test if AV equals lambda V. We just want to see this, right? So we do A times V. A is given here, 1, 1, negative 3, 5. And the V is given like in the row vector, but we can change this into like a column vector, 1, 3. Do the product. Let's see, the first row times this number vector, so 1 plus 3 should be 4. And the next is negative 3 plus 15, so should be 12, right? And we can simplify this vector. We can take the factor of 4 out, and we get 1, 3. So you can see here, it's like a V equals 4 times V, right? So V is the eigenvector. So we say V is an eigenvector. Okay, and you can try this exercise actually. So let's see. For this one, 1, 3, 2, 2, and for this vector, which is 1, 1, please test if V is eigenvector and find lambda. Okay, let's take a look. It's pretty easy, so let me do this quick. 1, 3, 2, 2. Do the product, so it's like 1 plus 3, 4. 2 plus 2, which is also 4. Factor the 4 out, 1, 1. So you can see this V is eigenvector, and what's the lambda? Lambda is 4. Okay, so this is the definition for the eigenvalue eigenvector. So we know the definition. Now let's take a look at how to solve eigenvalue and the eigenvector. So let's see how to find the lambda and this vector V. Let's take a look at the definition for lambda and V. So they should satisfy AV equals lambda V, right? And if we move them to one side, so it becomes AV minus lambda V equals 0. And we want to factor V out, but we cannot do A minus lambda, okay? Because this is matrix, this is number, scalar, right? So we do this way. So A times V minus lambda, think about like I as identity. Identity matrix times anything equals that matrix, right? Like what's the identity matrix? IA equals AI equals A. It's like a number 1, but it's for the matrix, okay, for the matrix. Identity matrix I2, which is 1, 0, 0, 1. And I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. Right? So they are called identity matrix. We learned this in I think 2.2 or 2.3, like terminology for the matrix. So we cannot do A minus lambda. So we do this way, okay? We times the I here, and now we can factor the V out. And because A can minus lambda now and equals this. Okay, this is a homogeneous linear system, right? Homogeneous linear system. And be careful here, V cannot be 0 because V is the eigenvector. Eigenvector cannot be 0. Okay, that's the definition for the eigenvector. And for the solution, if we use Cramer's rule, like for the solution, so we treat this as like it's like ax equals 0. You can think about that one. So, but here the matrix A minus lambda I is just different matrix, but that's okay. If we use Cramer's rule, if like A minus lambda I doesn't equal 0, if the determinant is not 0, so we can solve like a vk each component in the V vector sk going to be like bk determinant over determinant of A, but here A minus lambda I, okay, A minus lambda I is going to be 0 because bk will replace one column by all the zeros, right? Then in that case, if A minus lambda I determinant is non-zero, we can get what? So we can get V vector is going to be 0. But V vector cannot be 0. That means we must have A minus lambda I equals 0. Okay, A minus lambda have to be 0. If it's not 0, this linear system has only 0 solution. That's impossible. Okay, it's not definition for the V. So next, we are just going to use this equation to solve lambda and V. I'm going to show you how to do this. Okay. The region means V cannot be 0 because V cannot be 0. Not be 0 because the linear system has non-trivial solution if and only if A minus lambda I this equals 0. Okay, determinant. Now let's take a look at the steps. How to find lambda and V. First step, find lambda satisfying, okay, this equation. A minus lambda I determinant equals 0. Second, for each lambda I. Sometimes we may find several lambda, okay, and plug in lambda I, find the solution to this homogeneous differential equation, Vi. Let's take a look at definition. Let's take a look at example. Let's see, example 2. We have a 2 by 2 matrix. Find all eigenvalue and eigenvectors, lambda and V of this matrix. 5, -4, 8, -7. This is our matrix A. So let's see how to solve for lambda. Lambda have to satisfy A minus lambda I determinant equals 0. So first step, we need to set up this determinant. Okay, so let's take a look at A minus lambda I equals what? Determinant. Think about A minus lambda I equals what? A is this one. and lambda I. So for this step, we just write down detail here, but in the future, we don't have to write down this step. We can directly write down a minus lambda I. So when we combine, you can see it's like 5 minus lambda, right? And here -7 minus lambda. Because for the other two positions, they are all zeros, so we just do -4, same as before, like this. So this is a minus lambda I. How to find a minus lambda I? We just minus lambda in the diagonal position, like this. And for the other numbers, they keep the same. So in the future, you can write down this step directly. Now let's calculate this determinant. This 2 by 2 is pretty easy to calculate, right? So we just do AB minus AD minus BC. So by definition, 5 minus lambda times -7 minus lambda and minus -32. So I'm just going to plus 32. That's okay. Let's simplify this. This equals, after simplify, okay, I usually like to, we need to expand, let's see. But when I do expand, I like to simplify a little bit. I like a factor -1 here, factor -1 from here, and the negative become positive. So it's like we change this into lambda -5, and I change the factor -1 out, so become lambda +7, right? And plus 32. Why I do that? Because usually it's easy to see how to, do the product from this way. I like to change the position of lambda, okay? It's like multiple by -1. And let's expand. So lambda square, and the middle part should be plus 2 lambda, should be sum of those two numbers. And this number should be product of those two numbers. Simplify. Lambda square plus 2 lambda minus 3. And we make this equals 0 because lambda should satisfy this determinant equals 0. So we say we need to solve for lambda from here. So lambda equals lambda plus 3 lambda minus 1. Solve equation is like solve equation. So we find 2 lambdas. Lambda 1 is -3. Lambda 2 equals 1. Right? So we find 2 eigenvalues. So they are eigenvalues. Are you okay, everyone? How do we find eigenvalue? We set a minus lambda I, determinant equals 0, solve for lambda. This is the first step. Okay, first step always find lambda. Second step, for each lambda, we find corresponding eigenvector. So for lambda equals -3, we plug this into a minus lambda I. So a minus lambda I equals what? Look at A. Oh, you can look at from here, either way, okay? You can look at this, because this is also a minus lambda, right? Okay. So 5 minus -3 becomes 8. -4, 8. And -7 minus -3, so it should be -7 plus 3, which is -4. Simplify. What we are going to do, we are going to solve this linear system. We are going to solve this linear system. So this is like our matrix here, right? A minus lambda I. So we want to solve this thing. So we reduce this into row echelon. Because the second row is totally same as the first row, we can make second into 0, 0. And for the first row, we have to divide by 8 because we need to have leading 1. So -1/2. Right? So in our mind, actually, we should look at this as like 0, 0, 0, 0. Okay, in our mind, we can think about this way, but when we do a minus lambda I, we get this C. So now let's see what is our solution. This is like x1, x2. So we should have a free variable. Is that right? Let's say this is v1, v2. Okay. v1, v2. Who is the free variable? Same as before. So free variable should be the vector value who has no leading one. So should be v2 equals t. And how about v1? v1 equals positive 1/2 v2, which means 1/2, positive 1/2 t, right? So look at this. So this equals t. So move this to the right side, become positive and plus 0. So the other side is always 0, which is like this. And what is our solution? The vector we write down this way. Our vectors equals v1 1/2 t, t. And if we factor the t out, is like t 1/2 1. Okay, so this is our eigenvector. Okay, and here t is free variable. Now let's take a look at this for the other lambda. Let's do one more time. Okay. Lambda equals 1. So same thing, we look at a minus lambda I. Look at the determinant, the first step. 5 minus 1, which is 4. So it should be 4, negative 4. Let me do this way. 4, negative 4, right? And here's 8. And the negative 7 minus 1, so negative 8. Okay, let's solve this. Reduce into row echelon, 1, negative 1. The second row, 0, 0. So who is the free variable? We can say this is S or R, doesn't matter. You can use any letter you like. Let's use S. Okay. So let's see how to write down the vector. So I'm going to write down the vector the easy way. Oh, let's do detail. Okay. V2 is S. What is V1? V1 should be positive S. Is that right? When we move this to the other side. The other side of the equation. So what's the solution? Should be SS. If we take S out, S 1, 1. Same thing, S is free. So what's the other eigenvector, eigenvalues? So eigenvalues are 1 and negative 3, and the corresponding eigenvector, they are like this and this. Okay. Now let's do one exercise, and then we do 3 by 3 matrix. For this matrix, find lambda and v. Please try this by yourself. Okay. Compared to chapter 4, this chapter is pretty easy. It's just calculations. It's just calculation. So we just need to know the procedure and just follow the steps, then we can find the solution. But here we need to practice a lot. We need a lot of practice. Okay, so let me give you the solution, but I suppose you already finished this one. So first step, I'm going to find the lambda. How to find the lambda? I write down a minus lambda I determinant. Okay, determinant we do straight line. So 1 minus lambda, negative 3 minus lambda, and 6, 2. Simplify. This equals 1 minus lambda -3 minus lambda minus 12. And same as before, as I said, I simplify this lambda minus 1, lambda plus 3 minus 12, because this is easy to do the product. X lambda square plus 2 lambda minus 3 minus 12. Simplify. Lambda square plus 2 lambda minus 15. Set this equals 0 and factor this out. So lambda should be 3, 5. So plus 5 minus 3, right? So lambda 1 equals -5. Lambda 2 equals 3. Okay, that's the first step. Second step, for each lambda, for lambda equals -5, plug into a minus lambda I, which equals, so 1 minus -5, 1 plus 5, 6. -3 minus -5, -3 plus 5 should be 2. Simplify, 1, 1, 0, 0. The solution, I'm going to write down the solution pretty quick. I have a free variable, which is the second component, t. So the first one should be -t, and you factor t out, so t -1, 1. Okay, that's the eigenvector corresponding to lambda equals -5. For the lambda equals 3, same thing, I plug in a minus lambda I. Now I need to look at my a minus lambda I. So 1 minus 3, so -2, 6, 2. -3 minus 3 should be -6. Simplify, 1, -3, row echelon. This kind of matrix usually is pretty easy to make into row echelon because it's always has like same row. Let's see what's the solution to this one. Second component is the free variable, so I say s, and the first one should be 3s, which is 3. If I take the 3 out, so it should be s 3, 1. This is the eigenvector corresponding to eigenvalue lambda equals -5. So not difficult, right? Pretty easy.